The Hessian matrix is a fundamental tool in multivariable calculus that helps us understand the behavior of functions at critical points. For a function of two variables, f of x and y, the Hessian matrix contains all second-order partial derivatives arranged in a specific pattern. These second derivatives are arranged into a 2 by 2 matrix called the Hessian. We build this matrix systematically, placing each derivative in its proper position. For functions of three variables, the Hessian becomes a 3 by 3 matrix. Each element represents a second partial derivative with respect to the corresponding variables. The primary purpose of the Hessian matrix is to classify critical points of a function. It tells us whether a critical point is a local minimum, local maximum, or saddle point. The Hessian matrix encodes crucial information about the curvature of the function at any given point. This curvature information is what allows us to determine the local behavior of the function near critical points. The eigenvalues of the Hessian matrix provide a powerful way to classify critical points. The signs of these eigenvalues tell us exactly what type of critical point we have found. There are three fundamental classification rules. When all eigenvalues are positive, we have a local minimum. When all eigenvalues are negative, we have a local maximum. When eigenvalues have mixed signs, we have a saddle point. Let's examine each case in detail with two-dimensional examples to understand how these eigenvalues relate to the curvature of functions. In our first case, we have a Hessian matrix with eigenvalues 4 and 2, both positive. This creates a bowl-shaped surface where the critical point is at the bottom, representing a local minimum. Now let's examine what happens when all eigenvalues are negative. When both eigenvalues are negative, we get the opposite situation. The Hessian matrix now has eigenvalues -3 and -2. This creates a hill-shaped surface where the critical point is at the peak, representing a local maximum. The most interesting case occurs when eigenvalues have mixed signs, creating a saddle point. In the saddle point case, we have mixed eigenvalue signs, +2 and -3. This creates a surface that curves upward in one direction and downward in the perpendicular direction, resembling a horse saddle. Let's now examine how these eigenvalues directly relate to the curvature of the function surface. The eigenvalues directly control the curvature of the function surface. Positive eigenvalues create upward curvature, while negative eigenvalues create downward curvature. Watch how the curve changes as we vary the eigenvalue. Understanding eigenvalues gives us complete information about critical points. The signs tell us the nature of the critical point, while the magnitudes tell us how sharp or gentle the curvature is in each direction. In two dimensions, we can analyze the Hessian matrix without explicitly calculating eigenvalues. The key is to use the determinant test, which provides a direct way to classify critical points. Case 1. When the determinant is positive and f(x(x) is greater than 0, we have a local minimum. The function curves upward in all directions around the critical point, creating a bowl-like shape. Case 2. When the determinant is positive but f(x(x) is less than 0, we have a local maximum. The function curves downward in all directions, forming an inverted bowl or hill shape around the critical point. Case 3. When the determinant is negative, we have a saddle point. This means the function curves upward in some directions and downward in others, creating a saddle-like shape that is neither a maximum nor a minimum. In three dimensions, analyzing the Hessian becomes significantly more complex. We need to examine all three eigenvalues or use alternative techniques like Sylvester's criterion. The determinant test alone is insufficient for three-dimensional analysis. In our analysis of Hessian matrices, we sometimes encounter special cases called degenerate Hessians. These require different approaches than the standard eigenvalue analysis we've discussed. A degenerate Hessian occurs in two main scenarios. In two dimensions, it happens when the determinant of the Hessian matrix equals 0. In higher dimensions, it occurs when the matrix has at least one eigenvalue equal to 0. Now let's see what happens when we have a truly degenerate case. When the determinant is 0, our standard classification method breaks down completely. When the determinant is 0, we cannot use our standard classification rules. The second derivative test becomes inconclusive, and we need additional methods to understand the behavior at the critical point. Let's examine a concrete example. Consider the function f of xy equals x to the fourth power plus y squared. At the origin, this function has a degenerate Hessian matrix. Now let's compute the Hessian matrix. The second partial derivatives give us a matrix where the determinant is 0, making this a degenerate case. When faced with a degenerate Hessian, we must look beyond second derivatives. Higher-order derivatives and alternative methods can help us understand the true nature of the critical point. For our example function x to the fourth plus y squared, examining the fourth derivative reveals that the origin is actually a local minimum, despite the degenerate Hessian. This demonstrates why additional analysis is crucial in these special cases.